Let's solve two problems which is from the 2018 Malaysia Mathematical Olympiad. So we have two problems over here, and before we start solving this problem, I want to point out that most importantly, Malaysia is actually the country where I live in. So the first problem over here will determine how many integers n are there such that the following expression, which is n to the power 4 plus 2n cubed plus 2n squared plus 2n plus 1 is a prime number. So we'll first solve this problem and then we'll proceed to the second problem. So in this problem over here, by just looking at the problem over here, we'll first note that it is quite intuitive to try to factor out this expression over here, because if this expression is factorizable, then it ultimately will limit the possibility of the integers n, since in order for a prime number to be a prime number, the factors must be only 1 n itself. So to begin, I'll try to rewrite this expression over here, which is n to the power 4 plus 2n cubed plus 2n squared plus 2n plus 1, and then I will try to factorize it. Well, to determine its factors, you can actually try to find the root of this polynomial. So you may guess the root by using the well-known theorem, which is the rational root theorem. And then by looking at this polynomial over here, the possible roots are just the roots plus or minus 1. And then by trying these two, you may find that -1 is actually a root of this polynomial. So therefore, this means that there must be a factor of n plus 1. And now, in order for the leading coefficient to be n to the power 4, there must be a n cubed, which is the leading coefficient in another factor. And then for the constant part to be plus 1, you must have a plus 1 at the end. And then for the remaining terms, you may try to find it yourself or just guess them. But playing around, you see that you have that this is n squared plus n, because you may see that originally we have that an n cubed term over here, because n to the power 3 times by 1, there is an n cubed, and then you want to have another n cubed term, so you must have that a term with n squared, so that you multiply by the number n in order to make it n cubed. But then now you notice that n squared term over there will contribute an n squared term, so you need another n squared term to make it into a 2n squared. And so therefore you need an n term over here. And then we see that this polynomial over here can actually be further factorized, where you can just try the rational root theorem, and also the candidates are just plus or minus 1, and then you find that minus 1 is also a root. So therefore there must be another factor of n plus 1. And now you have n plus 1 squared, and then you have that this is n squared plus 1. Well, you can just try yourself to factorize it. And then now in order for it to be a prime, which over here you see that this is a prime, well, I will consider two cases. Well, for the first case, we have that n is equal to 0. And in this case, if n is equal to 0, we see that this quantity n plus 1 squared times by n squared plus 1 is actually just equal to 1, which is not a prime. And so when n is equal to 0, the whole thing is really not a prime. And then for the second case, I will consider n not equals to 0. In this case, you note that n squared plus 1 is greater than 1. So therefore, this shows that we have the factor n plus 1 squared must be equal to 1 in order for it to be a prime, because a prime number only has the factor 1n itself. So therefore, the candidates for n is just n equals to -2, because n is not equal to 0 in this case. So you have to have -1 squared to be equal to 1. And so we see that this shows that therefore the only possible n in this case is actually just n is equal to -2. So this means that there is only 1n. And so 1 is our answer to the first problem over here. And now let's look at the second problem. So for the second problem, we prove that the following number, which is 9 to the power of a1 plus a2, the whole quantity, times by a2 plus a3, times by a3 plus a4, all the way to a of 98 plus a of 99, times by a sub 99 plus a of 1. And subtracting 1 from this number will show that this whole number over here is divisible by 10 for any choice of positive integers a1, a2 up to a of 99. So in other words, regardless of how you choose all these 99 numbers over here, the number above must be divisible by 10. So to show this, we'll use a proof by contradiction, where we first assume, for the sake of contradiction, that there exists 99 numbers, which is A1, A2 up to A of 99, such that we have that the number 10 does not divide 9 to the power of A1 plus A2, A2 plus A3, all the way to A of 99 plus A1, the whole thing minus 1. And so this tells us that we write this statement in the form of modulo congruence. So this means that we have that the following holds, which is -1 to the power of A1 plus A2, A2 plus A3, all the way to A of 99 plus A1 is not congruent to the quantity 1 modulo 10. And so this means that -1 to the exponent, which is A1 plus A2, A2 plus A3, all the way to A of 99 plus A1 must be congruent to -1 modulo 10. Because the exponent is an integer, and then -1 to the power of any power which is an integer is just equal to -1 or 1. So in this case, because it is not equal to 1, so it must be congruent to -1. And then what this tells us is that we will have that the exponent, which is A1 plus A2, A2 plus A3, all the way to A of 99 plus A1 is odd. Because if it is even, then the whole thing will be congruent to 1, which is not true. This tells us that A1 plus A2, A2 plus A3, all the way to A of 99 plus A1 are odd integers. So now we'll derive a contradiction over here, which we'll then see that we'll add up all these integers, so we'll have that A1 plus A2 plus A2 plus A3 plus all the way to A of 99 plus A1, and this is equivalent to, we'll have that this is 2 times by the sum of all the AIs from A1 to A of 99. And then this is an even integer. But then note that this is a contradiction, because what we have originally is that all of these are odd integers. And most importantly, you see that this is equivalent to the sum of 99 odd integers, which is an odd integer. So this is obviously a contradiction. So this tells us that for all A1, A2, A3 up until to A of 99, regardless of how we choose them, we must have the quantity 9 to the power of A1 plus A2, A2 plus A3, all the way to A of 99 plus A1 minus 1 must be divisible by the number 10. So therefore, this proves the second problem. Now we are done for these two problems. So if you want to solve more Malaysia Mathematical Olympiad problems, then be sure to check out this video over here.